Hi, my name is Dave Williams and I'm a second-year PhD student in the UCL Solar Research Group. In this video, I'll be presenting our paper on deploying automated program repair at Bloomberg, which introduces a new format for integrating tool-generated patches directly into the code review process. By the conclusion of our study, the tool we developed through our research, which we called bAssist, was already being used daily by several hundred Bloomberg engineers across over 1,000 repositories. So in this talk, I'll be going through our journey for how we created bAssist, from the design phase where we came up with our concept, to how we implemented and evaluated it based on software engineer feedback. Let's look at a bit of background first. APR tools share the common trait being that their output is usually a patch which software engineers need to review before applying to their code bases. Prior studies on the deployment of APR have reported strong patch acceptance rates of between 40 and 50%. However, these numbers were recorded in conditions where developers were predisposed to using these tools, and in another instance, a tool recently deployed at Bloomberg only had acceptance rates of between 5 and 8%. This much weaker result suggests that the way in which we present automatically generated patches is crucial to consider when the goal is to achieve the widest possible adoption for a new APR tool. If we take a look at the architecture in which we were developing our novel approach, we can see that Bloomberg already had an existing tool in place called RSAT, which triggers as part of their continuous integration pipeline. When triggered, this tool essentially runs a multitude of other tools, including classic static analyzers, such as ClangTidy, as well as more complex APR tools like FIXI. It then combines their outputs into a centralized fix report for the current repository as of the last commit. The primary issue with RSAT in its current state, however, is that once this fix report is generated, it's stored somewhere deep in the Jenkins output pages, and the only way for developers to apply these patches would be to manually retrieve and download this report to apply the changes locally using Git. While some engineers have been okay with this approach, others we talked to were sometimes entirely unaware of RSAT's purpose, or at least weren't using it to its full potential. By examining this workflow, we identified three key factors affecting patch acceptance. The first is timing. Patches should be presented to engineers when they are receptive to feedback on their work. For instance, a natural time for this would be during code reviews, where the purpose of the discussion is to ensure that any new code being written is both of high quality and aligning with the higher design goals of the software. In terms of audience, this has everything to do with the location in which the patches are presented, meaning patches are more likely to be accepted when developers who are familiar with the code are reviewing them. And finally, it is also crucial to consider what code is being targeted. Developers are unlikely to want to review patches targeting code they aren't currently working on, since it takes them out of the flow of developing a new feature. So essentially, we wanted to find an intuitive format which combines these three factors while allowing developers to accept and reject fixes easily. To meet these criteria, we looked at GitHub suggested changes. Suggested changes are a relatively new feature in GitHub, which allows developers to propose modifications directly within the pull request user interface. As you can see, these changes appear just like any other comments, and suggestions can only be made on lines of code modified in the current PR. In terms of its value, developers are able to accept with very little effort, and can even modify the suggested change manually within the interface before committing the change to their codebase. Developers can also reject these just as easily if they feel the change is either incorrect or does not adequately address the issue in their code. Keeping suggested changes in mind as the medium through which we could present APR-generated fixes, we devised a concept for our tool, which we called bAssist. By using this patch presentation format, we can directly integrate the APR tool output into the current pull request, meaning developers can interact with this feedback in the place where code review discussions usually occur. In our concept, bAssist would listen for when new RSAT reports are generated, extract the relevant patches from the fix reports, and convert these into suggested change comments which it then posts to the corresponding pull request using GitHub's REST API. If we now return to the patch acceptance factors which I mentioned previously, by presenting patches to developers in the same pull request they are currently working on, we're able to address all three simultaneously. For timing, these suggested changes are posted shortly after the CI checks are completed, which is a time when developers are usually expecting feedback on their code. This means the resulting patches can be reviewed during the regular code review process. In terms of audience, we assume that the engineers who are reviewing the pull requests are already those who are familiar enough with the codebase to confidently decide whether a suggested change is useful or not. And finally, for context, BAssist only extracts the patches in the RSAT report which target the green lines of code in a pull request. This greatly increases the likelihood that reviewers will find these patches relevant, as they are related directly to the code that has recently been changed and already requires careful review. In this way, BAssist can act as a sort of peer reviewer on a pull request, creating suggestions in the same way that reviewers typically would. Now, if we zoom out a bit and look at the big picture again, we can see that BAssist bridges the gap between developers and tool output seamlessly. I want to stress the importance of this, as I feel one of the key contributions of our paper is that essentially any novel tool which generates patches in a unidiff format can use the same suggested change medium to intuitively present users with their fixes. Once we had finalized our concept for BAssist, we decided to present this to engineers through a survey to gather the initial thoughts of how willing they would be to adopt this in their workflows and to what extent. From the pie chart on the left, we can see that over 40% of respondents stated the current pull request would be their favored place to fix issues during code reviews, with another 29% suggesting they wouldn't mind adopting this format either. The graph on the right indicates how many suggestions engineers would be willing to review on a pull request. Most responses lay between 5 and 10 suggestions, meaning that while developers are definitely willing to review such suggestions, tools need to adopt a quality over quantity approach and try to suggest patches which will almost always be useful. This study informed our implementation priorities and gave us the go-ahead to start developing a prototype of BAssist. And once this prototype was complete, we sat down with 11 engineers and showed them 10 examples of suggested changes generated by BAssist to see how they would react if they saw these changes on their pull requests. For each change, we asked developers 3 questions: how they would respond to the change, how useful they find each change on a 5-point Likert scale, and finally if they would prefer a simple text comment warning them of the issue as opposed to a suggested patch. Looking at the results from this study, we can see that acceptance rate varies greatly depending on what type of issue is being addressed. For formatting and dependency management examples, engineers were very quick to accept these changes, as they believed the tools making these suggestions are trustworthy. For code correctness and best practices, while the feedback is more nuanced, we still see positive results. The acceptance rate being over 55% is a great result compared to the previous studies I mentioned at the beginning of the presentation, but the one I want to focus on more is the fix it in my own way column. While this may initially indicate a neutral or even negative reaction, I believe this can also be seen positively. If BAssist is alerting developers of potential issues in their codebase, even if it cannot suggest a usable patch, it still allows for more issues to be addressed overall and will result in a cleaner codebase regardless. I also want to note that engineers consistently found the patches useful, with an average rating of over 4 for each type of issue, and that they preferred having a patch as opposed to a simple text comment in almost 90% of cases. So, to summarize our findings, we identified timing, audience, and context as the 3 most important factors to consider when thinking about how to present APR tool output to users. We also learned from our first study that tools should try to be consistently useful, and the low number of patches engineers are willing to review suggests that minimizing false positives is a top priority when developing new APR techniques. Finally, we found that when they are presented effectively, patch suggestions can almost always be useful to engineers, regardless of whether they directly accept the patch or not. There are, of course, many more points in the full text which I would strongly recommend you read if you intend to work on a new APR tool. As I mentioned at the beginning of this presentation, BAssist has been a great success and already had several hundred daily users by the time we wrapped up our interviews. That's all I wanted to present to you today. I hope you found this presentation interesting. Please feel free to scan the QR codes on the right, which will take you to our ACM and archive publications respectively. If you have any questions about the work itself, or about future collaborations, you can contact me through the links at the bottom of the slide. Thank you for listening.